Thank you very much. So welcome everyone. So today I'm going to talk about surface enhanced Raman spectroscopy as we had previously, which is a highly sensitive optical method for trace detection. So before we dive into it, I want to give a short introduction on light scattering. So scattering is describes processes where particles or radiations, such as light or sound, are forced to deviate from their straight trajectory. And since we are here talking about optical measurements, I will focus, of course, on light scattering. So first of all, there are three main domains of light scattering that can be distinguished by the relative size of the scattering particle, which I will name P, and the wavelength of the light, lambda. So first of all, there is the geometric scattering regime, which is the case when the scattering particle is much, much larger than the wavelength of the light that is being scattered. Here we have the classical case, incoming angle equals outgoing angle, and you have a very weak wavelength dependence, which means that the strength of the scattering of the individual photons, so how many photons are scattered, is not really dependent on the wavelength of the photons, as long as, of course, the wavelength is much smaller than the scattering particle. There's the second domain, which is referred to as me scattering domain, which describes when the particles that scatter the light are approximately at the same length scale as the wavelength of the incoming photon. Here we have a rather complex scattering behavior and asymmetric scattering directions. We still have a weak wavelength dependence in this case, so it's still the strength of the scattering is not very strongly dependent on the wavelength. And last but not least, the Rayleigh scattering domain, where we have scattering particles that are much, much smaller than the wavelength of the incoming light, which again has a symmetric scattering geometry. And here we have a very strong wavelength dependence, which means that shorter wavelengths are scattered much more strongly than longer wavelengths, which is also why the sky is famously blue, because when you look up, you see a lot of short wavelength blue light being scattered into your eyes. This gives the sky the blue appearance. And this is actually the regime where also Raman scattering takes place, which is the case when, for example, we scatter light particles or molecules, which are very small in size, much smaller than the wavelength of the light. So let's dive a little bit more into this Rayleigh scattering regime. So usually when light is being scattered by small particles, most photons get scattered elastically, which means there's no energy exchange with the sample or with the sample molecules. And there is also 1 in a million photons is a special photon, which is getting Raman scattered, so actually it gets scattered inelastically and has an energy exchange with the sample. Down below, we see an image, just a schematic drawing of incoming light with some sample molecule, and it gets scattered, so it changes its direction, but it doesn't change its energy. And the inelastic scattering means that the photons that get scattered by the sample molecules either get scattered with lower energy, which means longer wavelengths, which is the Stokes Raman scattered light, here indicated in red. And there's also a portion of the light that gets anti-Stokes Raman scattered, which means that it actually has a shorter wavelength after the scattering process, and thus a higher energy than the initial light. And very importantly, the amount of energy that's being exchanged with the sample molecule is very much dependent on what molecule is doing the scattering, and thus we can get a chemical fingerprint of the measured sample by looking at the individual energy losses of the Raman scattered light. Here, just to make it more clear, there's another picture. Here we can see, again, the picture of the molecule with the scattered lights, and we also have a graph showing the wavelength on the x-axis. And in the center here is a large peak of the Rayleigh scattered light. So most light is getting Rayleigh scattered, and shifted to longer wavelengths are the Stokes Raman lines. So these photons at this individual wavelengths are getting Stokes Raman scattered. So they have a lower energy, so they leave some energy inside the sample. And we also have the anti-Stokes Raman lines, which have a shorter wavelengths, thus a higher energy. So they took some energy from your sample. It is important to mention that under normal conditions, as we also see here, the probability for Stokes Raman scattering is much, much higher than for the anti-Stokes Raman scattering. That is why usually Stokes Raman lines are being measured and are just referred to as Raman lines, just to keep the name short. So we leave out the Stokes or the anti-Stokes. Another representation to look at this is the energy state representation, which we see here. Here we have the energy states of the sample that we're illuminating, indicated by horizontal black lines. We have individual photons that interact with the sample, shown as arrows. So the arrows that are pointing upwards means that the photon comes in. Arrow going downwards means that the photon comes out. We can see the Rayleigh scattering in the energy state representation. We go from some state here, from the ground state that with the number 0. We go up to a virtual energy state, and the photon immediately gets released, and the molecule or the sample goes down to the same energy level, so the arrows have the same length. In the Stokes-Raman scattering case, we go from a low energy state to this virtual state, and then we go back to a higher energy state, here to the first state in this case, which means the arrow of the photon going in is longer than the arrow of the photon going out, which means the energy of the incoming photon is higher than the one going out. In the anti-Stokes-Raman scattering case, we have the opposite. We start from a higher energy level, go up and then go down to a lower energy level, which means the photon gains some energy. And here we can also see the link to infrared absorption. So what we do in infrared spectroscopy, which is also widely used for chemical analysis, optical chemical analysis of different samples, we fire infrared photons onto the sample, and these photons get absorbed directly by the sample and lifted, so to say, from a lower energy state to a higher energy state, indicated by this small arrow. So we can already see the energy of the photons is much smaller. We have a much smaller arrow and there's no photon coming out. So the molecule is not giving off another photon and falling down to the ground state, but it's just being absorbed, going to the first state. By the way, do you even see my mouse? I will just activate the laser pointer to be sure, so you see where I'm pointing it.
All fine.
Okay. With this cleared, now let's talk a little bit about the Raman spectroscopy instrumentation. So how are we going to use this Raman effect to get a signal from our samples? In order to measure the energy loss of the inelastically scattered light, we actually need to know the initial energy of the light precisely, of course. Otherwise, we cannot calculate the difference. And also, since only 1 in a million photons is being inelastically scattered, we need, in order to get a good signal strength, we need a very high light intensity. So what we need is a monochromatic, high-powered light source. That's why we use lasers, because they're perfectly good for this application. And on the right side, you can see a schematic setup of a Raman measurement. So what we do is we take a monochromatic laser of a certain wavelength. We shine onto the sample. The scattered light is being collected. What we then need is a laser filter to filter out all the Rayleigh scattered light with the wavelength of the laser, because otherwise it will just overpower all the Raman scattered light. So what is left after the laser filter is just Raman scattered light. This light will then hit the grating. The grating will spectrally resolve the light into different wavelengths, and we have an array detector with individual pixels, each pixel measuring a different wavelength. And when we plot this, we get a nice Raman spectrum. So the Raman spectrum is schematically shown here. We have the intensity on the y-axis, which gives you how many photons are there. And on the x-axis, we have the Raman shift, which is usually measured in wave numbers or 1/centimeters, which gives us the energy loss of the photons that hit the detector. So this is a nice measurement technique with many advantages, which make it usable in many industrial applications, and it has been used for decades now. The advantages are it is non-destructive, contactless, and also real-time capable, so it's very comparable in some ways to infrared spectroscopy. It also has, of course, as everything, some downsides and limitations, which is, for example, it's not applicable for every sample. Often we have the problem of fluorescence overpowering our Raman signal, and then we can measure nothing with our Raman spectrometer. And another problem is at larger working distances, we get very weak signals. So if you want to measure from far away, Raman spectroscopy might not be the method of choice. And here's just some pictures of different types of Raman spectrometers that are out there. We can have a classical tabletop Raman spectrometer connected to a Raman measurement probe. There are also handheld devices, which you can take, for example, in the industry is often used for controlling of substances that you import into your company. You want to check is it really what I think it is? You hold the device next to it, click measure, and it tells you what it is. And you also have Raman microscopes if you want to measure very Raman spectra of very small spots in some microscopic samples. So now I want to show you a Raman spectroscopy measurement example that we did a couple of years ago. Here we have Raman spectra of two substances plotted in one graph. Again, on the x-axis, there's the Raman shift corresponding to the energy loss of the individual Raman scattered photon. On the y-axis, we have the amount of photons, and we have a blue line for milk powder and a green line for melamine. And we can see clearly these two signals look very much different. For example, the melamine has distinct peaks at 582, 675, and 983 wave numbers. And we can clearly distinguish these two substances from one another just by looking at their Raman spectrum. So this can, of course, be exploited to measure melamine contaminations, for example, in the milk powder, which we can see in the graphs here on the bottom. We have graphs from milk powder mixed with melamine powder in different concentrations from 0 to 10%. And on the very right side, we can see a zoom in on the characteristic Raman band at 675 that is only present in melamine and not in the milk powder. And we can see the more melamine is in the sample, the higher this peak is. And we can go down to a concentration of about 1%. And after the 1%, we cannot see the Raman signal anymore because the concentration is just too low. So in this case, we have a limit of detection of approximately 1%. This is also the concentration regime where traditional or conventional Raman spectroscopy thrives. So in the percent range, we can use Raman spectroscopy perfectly fine to measure the concentration of substances in the percent range. But now I want to talk about surface enhanced Raman spectroscopy, which will allow us to get these limits of detections down to the ppm level or even lower. So first of all, what is surface enhanced Raman spectroscopy? It's usually abbreviated as SERS since it's such a long word, so I will call it SERS from now on. It uses surfaces of tiny metal structures, such as roughened surfaces, nanoparticles, or nanotubes for signal enhancement of the Raman scattered light. So theoretically, we can get up to a factor 10 to the 11th power stronger signals. This effect already discovered like 50 years ago in the 1970s. And still there are two theories around explaining the effect, which are still highly debated in the literature. So the more popular theory is the electromagnetic theory. This theory states that the electric field enhancement via localized surface plasmon excitation is responsible for the strong enhancement of the Raman scattering. It states that the enhancement happens with the incoming and the scattered light. So it would lead to a double enhancement. This is also where this factor 10 to the 11 comes from this theory. And the surface plasmons appear on metal surfaces with near zero band gaps. And in the chemical theory, the other theory that tries to describe the effect, they say that the resonance Raman spectroscopy explains this enhancement. And the high intensity comes from charge transfers from the metal surface to the adsorbing species. And this effect is relevant for nanoclusters with considerable band gaps. So the two bold printed statements actually contradict each other. So this is where the theories don't agree. And since there has been no experiment yet been able to distinctly say one or the other is true, we still don't know, and most likely both effects appear in combination. At least that would be my guess. But anyways, we don't know exactly why it works. We know that it works, which is the more important part. So let's dive into how we can use this SERS effect to our advantage. So in order to exploit this SERS effect, the sample has to be in very close contact with the nano structure or nanoparticles. And there are basically two ways this is done. So the first one is I will refer to as a liquid SERS, which is when you have a nanoparticle solution. So you have your nanoparticles in some form of liquid solution. And what you do is you put your sample inside this nanoparticle solution and have them mixed together. So now your sample that you're interested in is mixed in with the nanoparticle solution. And what you do now is you just make a measurement inside this solution where the analyte, so the sample is in close contact with the nanoparticles, and you get a much stronger Raman signal this way because of all these nanoparticles that are in the solution now. The second way that is usually done is using SERS substrates. So what you do here is you have a substrate and you have some nanoparticles or a nanostructure on the surface of the substrate, and you put your sample directly onto these nanoparticles or nanostructure, and then it is mixed in there and in, of course, in close contact with all the nanostructures. And what you then do is you take your Raman measurement onto this surface. So you measure on the surface of your substrate, and there you can take full advantage of the SERS effect and have your strong signal enhancement. These two have their advantages and disadvantages, as always. The advantage of the liquid SERS is you can use very high laser power for the measurement, because the higher your laser power, the higher your signal will be. It is not really possible with realistic laser powers to destroy your liquid nanoparticle solution. And also the signal strength is independent from the measurement position inside the liquid. So as long as you measure somewhere, you will get the same signal, since everything is homogeneous in the liquid state. The disadvantage is that your sample gets, of course, further diluted in the nanoparticle solution. So if you have a sample with only trace amounts of some substance you're interested in and put it in further in solution, you will dilute it further, which will give you a lower signal. And also another problem is that the sample may not dissolve in the nanoparticle solution, and then you won't be able to measure it. The second approach, using the substrates, has the advantages that the amount of backscattered light, and thus also the amount of Raman scattered light, is much larger than for the liquid SERS approach. And also the sample does not get further diluted when you apply it to the substrate, because everything is solid here. The disadvantages are that differences on the measurement position are possible, because you don't know exactly how your sample will be placed on your substrate. So there might be some spots where you have more of your sample, there might be some spots where you have less of your sample. So it's not independent of the measurement position, your signal strength. And some SERS substrates can also be damaged when high laser powers are applied. So you simply use too high laser power, you burn your substrate and break it. And that's why you always have to be aware what is the maximum laser power you can use with your substrate. So now I want to show you a measurement example using liquid SERS measurements. Using liquid SERS, we were able to measure, for example, melamine in water down to a concentration of about 0.1 ppm, which is 0.00001% of melamine inside the water, which is 100,000 times more sensitive than a conventional Raman spectroscopy. So we definitely took advantage of the SERS effect. On the right side, you can see the Raman spectrum here zoomed in on the melamine band, on the very characteristic melamine band here, located at 700 something inverse centimeters. And we can see for the 0.5 ppm, we get a very strong signal still. For the 0.1 ppm, it is still noticeable that there is some melamine inside of our sample. Another measurement example would be that I can show you would be parathion in water. Here we have a larger concentration of about 24 ppm. And this parathion is actually a banned pesticide. It has been banned in the European Union since 2001, but is still used elsewhere in the world. And we can detect it using surface-enhanced Raman spectroscopy. So this might be a useful technique, for example, to check imported foods from other places in the world where they still are able to use parathion. And you can check if there's some residue of the parathion, if there's some leftover on your food, which you might not want to ingest because it can be harmful to your health. So after the liquid SERS examples, I want to show something about SERS substrates. So nowadays, SERS substrates are available from multiple different suppliers, but they vary very strongly in the terms of price. So you can have substrates that have cost a few euros to a few €100 per measurement spot. So this is quite a big range that is covered. Also, the signal enhancement and thus the limit of detection for certain substances is very much different for the different substrates. Ease of use is another big point. So some of them are more easy to handle and use than others. The damage threshold is also widely different. There's some substrates that can withstand high laser powers. There's others that you can burn quite easily using low laser powers. Also, the ideal laser wavelength is different for all the substrates. The measurement reproducibility might vary for substrates, and also another point is the background signal. So some substrates, even when they clean, give you a background signal which might interfere with your SERS measurement that you want to do. And here I want to show you shortly two other measurement examples using two different substrates. Again, the analyte, so the sample we measured was melamine in water. First of all, it's a very easy to use paper-based substrate where we used melamine, where we measured melamine in water down to a level of 2 ppm was possible with this substrate. And the limit here mainly was the damage threshold, because paper is easily burned by the laser light. We could only use about 10 milliwatts of laser power. And if we turn the laser any higher, then we burn the substrate and get no signal out of it. Another substrate that works much better in the terms of damage threshold is aluminum-based substrates. Here we can see the measurement of just 1 ppm melamine in water with different laser powers going from 3.3 milliwatts up to the full laser power of the system we used back in this measurement, which is 373 milliwatts. And you can see the peak of the melamine rises with higher laser power, as you would expect. And in the inset, you can see the height of the peak plotted versus the used laser power, and is a perfectly linear behavior, which means that the substrate is not broken at any point with high laser power. So we can use the full power of our system of 373 milliwatts of laser power, which means we can detect much lower concentrations than this 1 ppm using this kind of substrate, just because we can use much more laser power. So this is also something that should be considered when you want to measure something. What laser power can your system provide? And can you use the whole laser power with your substrate, or will you just burn it and lose your signal entirely? Another SERS substrate that we use quite frequently are glass-covered SERS substrates. They are covered with a gold nanostructure, and with these, we were able to measure melamine in H2O even down to a concentration of 0.01 ppm, which is another 10 times increase, for example, compared to the liquid SERS measurement. So these substrates can be used also to measure many other kinds of molecules. Here, just to show a few examples, would be E. coli bacteria, caffeine, arginine, amphetamine, ascorbic acid. And you can see just by looking at all these nice surface-enhanced Raman spectra that they all look different, so they can be clearly distinguished. And using the SERS effect, they can also be measured inside of your sample in very low amounts. So this brings me to a slide with just some different applications of SERS where it is being used today. So there are bio and medical applications, which includes the detections of proteins in body fluids. They can also be used as an early detection of cancer biomarkers. They can be used for bacteria and virus detection, and also for the detection of various diseases like Alzheimer's or Parkinson's disease. They are used in food quality analysis, for example, food contamination detection, as I mentioned earlier with the pesticide detection, or also water quality measurements can be done. In the pharmaceutical application, it's been used for drug testing and also for quality control. And forensic science, you can use it to do drug and narcotics detection in small amounts. You can use it to trace explosives. You can also use it to detect counterfeits. And last but not least, environmental analysis, for example, pesticide detection again, detection of heavy metals, for example, in soil, detection of micro and nanoplastics, which is a big topic these days, and also detection of harmful synthetic dyes that might have leaked somewhere in the environment. So this already brings me to the summary. So to summarize everything, I hope I was able to show you that surface-enhanced Raman spectroscopy is a powerful tool for trace detection. It allows to detect concentrations for less than 1 ppm, of course, depending on how you measure it and what the substance is. SERS can be also used for the detection of many different chemical species. So many different chemicals can be measured with it. And what you need is only a few microliters of sample for a single measurement. And in recent years, SERS saw a significant rise in terms of technical readiness level, and now can not only be used in scientific laboratories, but is also already used in industrial applications. And hopefully we'll see in the future many more applications in the industry. And the price of SERS measurements also has significantly decreased in recent years. Nowadays, prices down to a few euros per measurement are possible. And with the right equipment and measurement approach, these measurements can also be done fast and easy, even by untrained personnel. And yeah, we have the necessary resources available at RECENT. So if you have any interest or any idea what could be tried with SERS measurements, just contact us and we can tell you if SERS is the way to go to measure whatever it is you want to measure. So with this, I want to thank you for your attention, and I'm open to questions on the topic that might have risen during my talk. Thank you very much.